Hey everybody, I just want to talk to you about some of the terminology that we use in statistics. It turns out the terminology is really, really important. There's a lot of things that we use that we have specific words for that can make statistics a little hard to understand. And so that's where I want to start. It's also kind of the most important thing. It's the one thing we're going to use universally. And it can often be the thing that is hardest for students to absorb, or rather, not exactly hardest for students to absorb, but the most important barrier to understanding, right? If I'm using a bunch of jargon that you don't know, you're not going to be able to understand the bigger ideas that we're trying to get to. So we want to start with terminology to allow us to understand the ideas as soon as possible. So I want to start here with the main idea of statistics. So this right here is the main idea of statistics. We want to not have to sample an entire group or an entire group of things that we're trying to learn about because there are often too many of them. So for instance, I'll just use a basic example here. If we want to know something about every person in the United States, it's very hard to ask them all. In fact, it's very hard to even count them all, right? The Constitution outlines the census. It says we must take a census every 10 years, and we've done that for the entire life of the country. The last one in 2010, I guess the last one is 2020 now, but the one in 2010 cost $13 billion and took months of work. It is a huge project. And so we don't really want to do that, right? What we want to do is take a take a few of those people and hope that their properties generalize to the larger group, which we call the population. Um, and it turns out that in general they do. That if you take a large enough sample, which is to say the small subgroup of this population, that you can often generalize things about that sample to the larger population. And that's the idea. That's, in fact, the main idea of statistics, or at least the type of statistics that we're doing here. So a couple terms, a couple I mentioned already. So as my example, just imagine that we want to know how tall American men are and that we're going to survey 1,000 of them to about their height. And then I'll put each of these terms in that context. So the entire group we're generalizing about is the population. We are not going to actually talk to everybody in the population. What we're going to do is we're going to talk to a small subgroup of them called the sample. So our population here is all American men, and our sample is just the 1,000 that we surveyed. So just a small subgroup of them. There's, just for reference, there are about 200-ish million, maybe 220 million adults in the United States. So about 110 million men, or 110 million American men. We only talk to 1,000 of them, right? That's less than, it's 0.1% or so, or significantly less than that. Sorry, math is deserting me here, but we talk to significantly less than all of them, right? And so I'm going to jump over my bullet point here, but the idea is that we're going to talk to a small group and generalize about that group to the population. A couple more terms: sample size and variable. Sample size is just how many people we sampled. We will often need that number in our calculations. It turns out that a lot of how confident we can be in how well this data generalizes to a larger group depends on how many people we talked to. So we can be a lot more confident that our results generalize well if our sample is large than if it is small. So for instance, if we take a sample of 1,000 people, we would be much more confident in the results than if we took a sample of 100 people. The variable is the thing that we're studying. In this case, it's height, right? We asked how tall are American men. The thing we're asking about is height. And then two different terms referring to numbers about the sample or the population. They have different terms because it turns out that you have to treat them very differently, and I'll talk about why in just a second. But parameters and statistics, now conveniently, parameters describe the population and statistics describe the sample. I don't know if that was an intentional choice by whoever made up these words, but it turns out to be a really good mnemonic device, so you probably want to remember it that way. A parameter is just a number about the population, and a statistic is a number about the sample. That's it. They're the same thing, just about different groups. So if we're looking for the average height of all American men, that would be a parameter. If we're looking for the average height of the men in the sample, that's a statistic. Let me talk briefly about parameters and statistics and then ask some questions. So things you want to see about parameters that are a little bit confusing at first. Parameters are constant, they don't change. It doesn't, like who we talk to doesn't change the parameter. It has nothing to do with the parameter. The parameter is some fixed number that we don't know. It's a number that we're essentially trying to guess, estimate. Guess is maybe a little bit too vague. We're trying to estimate it from data, right? So if I'm looking for the average height of all American men, I won't know that before I start. And then when I take my sample and find out what the height is in there, I still won't know the parameter. All I'll have is a statistic. And parameters don't change depending on what sample you take, where you'll find when we talk about statistics in a second. And parameters and statistics are going to seem really similar, and they are in the sense that they're the same thing, but about different groups. And we have to treat them very differently because we don't know parameters and we do know statistics, but statistics are not the things that we actually want to know. We want to know parameters. We want to use the statistics to estimate what the parameters are. And again, we're almost never going to know the actual value of a parameter. Almost never. Sometimes you can sort of think you can have a pretty good idea of what the value of the parameter is. Like if you've done enough sampling, for instance, like average height of American men is actually fairly well known because there have been so many tens of or hundreds of thousands of American men who have reported their height to various things. And so we actually know that this right here, this number, 69.5 inches, is actually quite accurate. It's not the actual parameter, but it's so close that we just don't make any distinction between the two. But in general, we're not really going to know the actual value of parameters very often. Most of the time, we're going to be trying to estimate those from the data, which is the point of statistics. A statistic, on the other hand, changes depending on what your sample is. So for instance, if I take a sample of 1,000 American men and I get average height of 70.18 inches within that sample, that is a statistic. If I were to sample 1,000 other men, right, I put all these 1,000 in back in the pool, and I sample a different 1,000, I'll get a different average, right? And so that statistic the statistic that I get will depend on the sample that I took, whereas the parameter does not. That's the biggest functional difference between the two. I guess there's sort of a theoretical difference in the sense that we know what the value of a statistic is, and we're using that to estimate the value of a parameter, but we don't actually know the value of the parameter in general. And in general, you can assume that you have access to all the statistics for a relevant sample, right? So if you want to know, if I just tell you we have a sample of 1,000 American men, you can just take it for granted that we can calculate all the relevant statistics that we want about that we have all the data about that. And that's usually true. Whatever you're talking about, that's what you'll have written down essentially from your sample. So knowing these terms, we can rewrite that opening paragraph like this. The main idea of statistics is to use samples to generalize about populations. That's really the ultimate goal of what we are doing in statistics, is we are using small subgroups to try to generalize about the large full group. All right, I think I've said that enough times now. Okay, so for some practice for you, why don't you guys go ahead and pause the video and try and answer number 1 here. You can find this worksheet, by the way, in the module for the week, as well as in course resources if you'd like. This is the terminology worksheet. I think it's titled Chapter 1 Terminology. So I've got 3 samples here. I'm going to go ahead and pause for a second, and then I'm going to talk about the answers. So pausing. Okay, so I hope you paused the video and tried to actually do these things. Identify the population, sample size, parameters or statistics, and what variables are being studied. All right, so here's Lauren. Lauren is our biologist that we will be using whenever we're studying animals in general. She's studying giraffes in Kenya, and she's interested in, among other things, their height, age, and gender. So she observes 56 giraffes in 6 different locations, including 12 adult males, 14 juvenile males, 13 adult females, and 17 juvenile females. Okay, so let's identify these things. So the population. The population is the thing that Lauren is trying to generalize about. And it says that she is studying giraffes in Kenya. So Kenyan giraffes, that's the population. Her sample is the giraffes that she actually observed. So the 56 giraffes that she observed in 6 different locations, including all these subgroups here. That's her sample. The sample size is how many giraffes she observed. 56. Sample size is 56. If you want the difference between sample and sample size, by the way, sample is what or who, and sample size is how many. Right? So 56 is the sample size, and then the giraffes she observed is the sample itself. Parameters and or statistics cited in this problem. There are no parameters cited here. Everything here is a statistic. 56 is a number about the sample. It's the size of the sample. And all of these things, all of these numbers here are about giraffes that were in the sample. None of them are parameters. So 56 giraffes, 6 locations, I guess you could say is a statistic. Yeah, sure, I'll say that that's a statistic too, since it's about her sampling method. 12 adult males, 14 juvenile males, 13 adult females, 17 juvenile females. All of those are statistics. They're all about the sample. Variables being studied, well, it says that among other things, they're looking for height, age, and gender, or she's looking for height, age, and gender. So height, age, and gender would be the given variables, plus presumably you're not going to travel to Kenya just to get the height, age, and gender of 56 giraffes. You're probably going to want to know some other things about them, but I don't know much about giraffes. So when I wrote this problem, that's all I cited. So that's number 1. Okay, so for number 2, I want to identify the same things. So let's read the problem. Porter is a statistics student interested in the grades in statistics classes. And when I wrote this, I didn't specify here, but I meant statistics classes at SBCC specifically. He asks around the math lab and finds that of 36 students he talks to, 10 have A's, 7 have B's, 4 have C's, 5 have D's or F's, and 10 decline to answer his question. All right, let me pause for a second and let you identify those things. All right, so I want to identify the population. It says he is interested in the grades and statistics classes. So his population is going to be the statistics classes, or the people in the statistics classes. The grades are going to be his variable, which technically I'm doing later, but that's what he's interested in. The people he is talking to are members of the population, right? So the population is the people he's asking. So the people, so SBCC statistics students would be his population. The sample were the people he talked to, so the 36 students he talked to in the math lab. The sample size, 36. Parameters and or statistics. Again, there are no parameters here because, as always, we don't know parameters. What we know are statistics. So the number of A's, B's, C's, failing grades, D's or F's, and decline to states are all statistics, as well as the sample size. And what variables are being studied? Well, the only variable we talked about here was grades. So there you go. That's it. Now, in question 2 here, this sample, by the way, it sounds reasonable if you don't think too hard about it, but there's a lot of problems with how my hypothetical student here actually took his sample, which we'll talk about a little bit later. All right, and then for part C here, I'm going to pause for a second. All right, let's do part C. So Maria works at a hospital, researching ways to improve patient care and health outcomes. She is currently interested in optimizing the emergency department intake process. So she gathers data on the time it takes between when a patient arrives at the emergency department to when they actually receive care. Of the 381 cases she reviews, average time is 2.1 hours from presentation to treatment. Presentation is when you show up at the hospital. Okay, so we want to identify population, sample size, parameters or statistics, and what variables are being studied. So what does it say she's working on? She's currently interested in optimizing the emergency department intake process. So she gathers data on the time it takes between when a patient arrives at the emergency department to when they actually receive care. So the patients presenting to the emergency department is the population, right? She's interested in improving how quickly patients get care. And we're talking about all the patients going to the emergency department. So that's her population. For her sample, it says she reviews 381 cases. So that's her sample. The 381 cases she reviews is her sample. And 381, of course, is the sample size. Parameters or statistics. Well, the only other number cited here is 2.1 hours. That is, the average time is 2.1 hours from presentation to treatment. Now, you might be tempted to say, well, that sounds like the average time for the whole emergency department. No. This is specifically about the 381 cases, so that means this right here is a statistic because it's about the sample. As usual, there are no parameters presented. We don't know anything about the population. We can guess that the average time to treatment is probably about in the vicinity of 2.1 hours, but we don't actually know that. We have to do some statistics on that first. And what variables are being studied? Time to treatment. Time from presentation to treatment is the variable that's being studied. Okay, so I want to talk about a few things that went wrong in 1B. We're not going to spend too much time on this because the focus of our class is analysis of data rather than gathering good data. Now, as it turns out, let me jump back up here for a second and say that this paragraph right here is super, super important in the study of statistics in general, and we are going to ignore it entirely. For our purposes, we're just going to assume that our data is always good, which is that's a wildly unjustified assumption. The number one difficulty in real world professional statistics is getting a good sample. And we're going to ignore that because the first thing we have to do is learn how to analyze the sample before we start talking about whether it's any good, because you have to do analysis on it to figure out if your sample is any good. So you have to learn how to do the analysis first before you can really even talk about whether the sample is good or not. So just be aware of that. Like, keep that in your mind in the background, that everything you do in statistics is all about how good was your sample. And we're going to go ahead and assume, or we're going to go ahead and assume in general that our samples are good, but I want to talk about some of the ways they can be bad. So for instance, right here, Porter is going around the math lab asking people, what is your grade in statistics? He doesn't know everybody in the math lab, and so he's essentially walking up to strangers and asking what their grades are. So that right there is a huge problem. You can't ask people personal information out of the blue and expect to get a reasonable answer. That's just not a thing that's going to happen. It's a particular kind of bias called response bias, where the response to your question is likely to be biased. People who don't know you are probably not necessarily going to be inclined to tell you the truth. They'll probably tell you something that makes themselves look better, right? Say you've got a B+, but you think you did pretty well in that last test, and some random dude rolls up on you in the math lab and says, what's your grade in statistics? And you say, I got an A, right? Even though you really don't, you probably actually have a B, some variety of B, but you're thinking, yeah, what does he care, right? What's he doing? There's also a significant number of people who didn't respond. 10 people declined to answer his question, as they totally should. If somebody just walked up to me and asked what my grade was, I mean, didn't know I was a teacher, I would be inclined to tell them to go jump in a lake, right? Because that's, what are they doing? And so that's called non-response bias. When people don't respond to you, there is a chance that the type of person who would not want to respond to this question might like those sorts of people might all have something in common, and therefore you're missing that segment of the population, right? People with not so great grades in statistics might be less inclined to tell you what their grades are, right? So if you talk to 36 people and 10 of them don't answer your question, it's likely that those 10 probably didn't have a bunch of A's, right? A lot of those, like if somebody has an A in a class, they're going to be just say, I got an A, right? Why would they might be proud of that fact. Whereas people with D's or F's might be less inclined to state their grades, which means that his responses are probably going to skew high, right? He's probably going to get more people saying they have A's that as a proportion of the people he interviews than is actually the proportion in the population. He also just asks around the math lab one time. And so there's a problem with that, right? Since he is only talking to people in the math lab, the people in the math lab probably all share some characteristics, i.e., those are all people who are generally working hard. And here's the thing that I don't know if you know, but generally speaking, going to the math lab results in higher grades. So the people that you find in the math lab tend to have higher grades on average than the student population as a whole. And so just by interviewing only people in the math lab, it's very likely that Porter has gotten a bunch of people with higher grades than usual. Additionally, it's not exactly stated here, but it's sort of implied that he only does this once, right? So he goes to the math lab at a particular time. Well, if he found a bunch of students in the math lab at that time who were working on statistics, it's very likely that their class just got out. And that of the 50 something sections of statistics we have, I don't know if it's that many this semester, but of the many sections of statistics that we have, he's probably talking to people from just one or two of them, right? And certain teachers are going to have higher grades than others, and certain teachers will have lower grades. And if he happens to be interviewing a bunch of people who are in a class with higher grades than average, well, then his results are going to skew high again. If he happens to be interviewing a bunch of people from a class with lower grades than average, then they'll skew low. And so this data, because it has so many of these problems, is not usable. What he should really do here is throw everything in the trash and disregard all results. And if you have very questionable data that's been gathered in a variety of it has a variety of problems, you are much better off in the real world just throwing it in the trash and not using it at all. Because it's very tempting to think that when you have data, that data must mean something. But all these problems tell us that not only does it probably not mean anything, it's likely to be misleading. And so to avoid being misled, what you should do when you identify significant enough problems is just chuck your data in the trash and try it again, right, using better sampling methods. So that's really what he should do in this case. There's too many problems here. You should throw it all away. Yeah, and that's what I wanted to talk about. I think that's all I wanted to say about terminology. So I'm going to go ahead and stop this video right here. Stop the recording.